Hello, my name is Braeden Warnick, and this is the second video in a series showing the development progress of a Unity demo that I'm implementing alongside my written graduate thesis. If you're interested in learning more about the main ideas of my thesis and the start of this project, please check out the first video in this series. I've included a link to it in the description below. Now before I start talking about the updates and the progress made, I'll go over a short recap of my ideas on the work up until this point. The goal with my thesis is to establish that the possibility of an event can be effectively used in combination with hierarchical task networks to drive the behavior selection of an AI agent in a game or simulation. The first example in my written work focuses on a city/crowd simulation featuring student AI agents in a small college town, and how this combined framework can be used to make the agents more believable and/or expressive. The first video in this series covers a brief introduction of how HTNs and the possibility of an event could work together. But it mainly focuses on the simple city simulation I've built using a basic HTN that's modeled after the example in my thesis. The students operate based on a straightforward HTN planner that covers when to go to school, work, find food, go home, find something to spend money on, or sleep. The version that's shown in my first video uses only preconditions and randomization to drive behavior selection. Now while the first video focuses on the ideas that started this development and the foundational demo I've established before starting the integration of possibility theory, this video will cover the new domain used by the students that uses the possibility of future events to make decisions. The main difference between both forms of the simulation is that the basic example operates off of simple preconditions when choosing how to spend free time. If they can afford the most expensive option and it's open, choose it. If not, check if the cheaper option is affordable and open, and go home if it's not. The possibilistic example drives student behaviors based on a domain that accounts for preferences and business traffic. This allows students to pick their choices based on which option offers the best possibility of success, or in this case enjoyment. While the basic domain represents a quick and easy solution using an HTN, the possibilistic domain offers more believable and expressive behaviors with very little additional work. The possibilistic form of the simulation is also important because it establishes a completed demo that represents the first example situation that's covered in my thesis. Furthermore, this complete demo that uses my proposed framework is additionally significant because having a built demo in Unity with shareable code allows me to better demonstrate how the ideas in my thesis can be directly applied to code in a modern game engine. The first thing that needed to be added in order to make the domain in the demo align with the domain in the first example of my thesis was personal preferences for each individual student. When each student is spawned, they're given a random modifying value for each activity and for staying home. This modifying value represents their personal interest in spending their free time doing each one. Then, I added another personal preference variable for activities in general and for staying home that can be changed due to the next day's schedule. This way, the earlier they have to be at work or school the next day, the less likely they may want to go out that night. Besides the personal characteristics added to the students, I also had to represent the business traffic at each location so that the students can compare the traffic against their preferences in their decision. To do this, I looked at various bowling alleys and sports bars around my town on Google and wrote some logic to shift the traffic variables to reflect the hourly and daily trends in local business traffic. With both personal preferences and traffic levels accounted for, I started working on integrating the domain in my written example into the student class to replace the basic domain previously being used. Now, before I explain how I implemented this, I'll further explain a part of the written example I'm modeling this domain after. As mentioned in the previous video, the ultimate context equation that represents the possibility of a student enjoying their time at an activity is the probability the student has the time for the activity, and the probability the student has the money for the activity, and the probability the student prefers the activity or the constraint that there is a high customer volume at that activity at that time. Meaning that the possibility that a student enjoys their time with a selection of an activity is the minimum of the probability the student has the time for the activity, the probability the student has the money for the activity, and the maximum of the probability that the student prefers the activity, and 1 minus the probability there is a high customer volume at the activity. As I developed the domain for the student and how they decided how to occupy their free time, I treated the first two probabilities like absolutes based on preconditions. Meaning that the only way a student considers the options for spending money on their free time is if they have the free time currently, and if they have enough money for the options, but that's really no different than the base domain. The complexity of the new domain comes in when replacing the priority order of picking the most expensive option whenever available with a utility selector that implements the latter half of the possibility context equation in order to pick the best choice. I'm only using such a proposed utility selector for this one choice to keep the domain as simple as possible while still proving effective. I didn't want to rely on utility selectors everywhere in the domain so as to not increase calculation time unnecessarily. If the student determines that they have free time and they want to consider going out, then their domain enters the utility selector previously mentioned for how they should spend their time, which is where previous preconditions like cost and time are now considered. The later precondition check helps trim down the amount of utility functions ran in the selector when evaluating options. The selector then compares the utility cost for each remaining available option using their respective functions. The utility function for determining the possibility of enjoying time by staying home simply returns the sum of the home modifying value and the home preference value that was updated for the upcoming daily schedule. For the remaining utility functions, the function is simple. Since the other two probabilities are already checked in preconditions, all that's left to do in these functions is to determine the max between 1 minus the chance of high traffic at the activity and probability that the student prefers the activity. With these utility functions written and used by the HTN when the students decide how to spend their free time, I've established an example of how to integrate the possibility of future events into the decision-making process of an HTN. The demo also finally reflects the ideas and example that are detailed in my thesis. Now let's move on to comparing the two domains and what subtleties emerge from the difference in how the students select how to spend their time. The first thing I'd like to do in comparing the two different forms of simulation is show several differences in heat map screenshots for comparable days before talking through some video footage from both. For example, the image on the left is a screenshot of the basic simulation on a given night, while the image on the right is of the possibilistic form on the same night. You can see that although traffic is similar at the workplaces and school buildings, the traffic at the businesses is several intervals higher in the basic simulation. While this is more than fine regarding creating a simple visual representation of a crowd being alive, adapting the simulation to fit the first example explained in my thesis allows the crowd in the sim to be more expressive, with believable and relatable reasons behind each decision made. Assuming the basic simulation serves as a passable example of using an HTN to drive a crowd simulation, then the image showing the heat map for the possibilistic simulation also demonstrates that there are no inherent issues when integrating the possibility of an event into an HTN. More specifically, it shows that these students in the simulation behave in line with what I supposed in the first example of my thesis. Using personal considerations as well as business data, students can determine which option offers them the best possible chance for enjoying their free time using both individual and world data. This means that an HTN can still be used to drive most of an NPC's basic behavior, and that there will not be any direct risk to the already established domain if one wishes to integrate a utility selector based on the possibility of future events. While most of the behavior that is different between the two simulations are caused by these obvious additions of personal preferences, there is another behavior that I'd like to point out that emerged specifically from using the possibilistic utility functions. One thing I noticed while running the simulation was that sometimes students would leave home late at night to go to some activity. It didn't happen every time I ran the sim, and it was usually just a few students when it did happen. I initially thought that it was an error in my logic, or something wasn't getting set to the right value at the right time, but after checking my work, I realized that it's an emergent behavior from the possibilistic utility selector and functions. Here's a clear example that I grabbed from one of my runs that helps show what happens with a student that's heading home. Here we see a student heading home because at this time, they don't have responsibilities. They're off work for the day, just got out of class, and they're fed. But most importantly, they personally prefer to go home tonight, meaning they believe they have the best possibility of enjoying spending their time by going home compared to going out. However, on the way home they realize that the bowling alley should be dying down around now, and that the low traffic would actually offer them the best possibility of enjoying their time, and they change their mind. While most students demonstrate that the possibilistic utility selector is successfully integrated by simply going where they prefer in their free time, this is a clear example of them weighing the traffic of the location against their personal preferences as stated in my thesis. Before covering the development of my heat map tool, I wanted to state that I believe that this version of the demo proves that the core proposal of my thesis is true. The possibility of an event can successfully be integrated into HTNs as a method of deciding between branches. Furthermore, based on the visual data seen from my two forms of HTN domain, I believe the domain that uses such a utility selector is able to make more believable and expressive NPC AI in games and simulations. I believe this because the possibilistic version results in more believable heat map traffic, and it also features clear and reasonable decisions made by students considering the possibility of future options. I believe this framework can be used specifically in games and simulations, since this demo has been successfully implemented in Unity, which is a popular modern game engine. Now, beyond covering how the updated demo achieves implementing the example in my thesis into a tangible game demo, I'd like to additionally cover the development of my previously mentioned heat map tool that I use to better understand how the two domains manifest differently. After spending some time fixing up a few bugs, a decent amount of time adapting my ideas properly to code and to newly used features in libraries, I spent a bit of time building a toggleable heat map that could help me better visualize how these students were spending their time. While I refer to this feature as a heat map, it also serves as a height map due to some things I noticed during development. To keep it short, the heat map is made up of a collection of prefab cells. Each time a student enters one and passes through, it increases a local interaction count and then changes the material of the cell based on which interval the interaction count falls in. The intervals are cold, cool, medium, warm, and hot, with cold maxing at half the total number of students, with each interval doubling afterwards. While this heat map serves as a great tool in understanding the daily lives of these AI agents, I found that some understanding was skewed based on relying solely on the color of the cell. At some point, even if I use some formulaic gradient for the material of the cells, as the interaction count increases, the colors all become the same. My solution to this was to also increase the Y scale of the cell by a constant for each interaction. This way, while the heat map shows a lot of traffic at both the bowling alley and bar, I can easily identify which one received more. Now, with all this said and covered and reviewed, the first example of my thesis and the accompanying demo are done in development. While I may go back and review the written sections covering this example, as well as the code for the demo to add more quality of life features in the future, this is no longer the main focus of development. After I finish updating my written thesis with a technical write-up of this demo to better explain how to translate the proposed ideas into written game code, I will be working on formulating and finalizing my ideas on applying this framework to groups of agents. While I'm unsure if I will be able to finish a complete demo for the second example used to explain my ideas for group thinking with this framework, I will be working on one as soon as possible. I hope to post more updates about both my written work when I finalize my ideas for group thinking, as well as any partial progress updates for the next demo as I try to complete it before my final thesis defense this upcoming April. Again, my name is Braeden Warnick. This has been another video covering some material and development from my thesis focusing on possibilistic HTNs, as well as the demo I'm implementing alongside it, and I look forward to uploading more updates in the future. In the meantime, if you're interested in my work and reaching out, please feel free to check out my LinkedIn profile down below and share any comments, critique, or general feedback about my work and videos. Thanks.